Welcome, curious minds, to the deep dive. Today, I want you to step into a molecular world that's, well, anything but static. Imagine these bustling chemical hubs where partners swap, electrons leap, and structures twist and turn. This isn't just theory, it's the dynamic reality of coordination complexes, and we're about to take a deep dive into their incredible reaction pathways. Our mission today is to really unpack the secrets behind coordination chemistry, reactions of complexes, drawing our insights from Shriver and Atkins Inorganic Chemistry. We're aiming to move beyond just knowing what happens in these reactions to truly understanding how and, crucially, why they occur. Yeah, the core idea is getting a real grip on the reaction mechanisms. We'll be looking at how ligands swap places, how electrons transfer in redox reactions, and even how, light can kick off totally new chemical events. So if you're studying inorganic chemistry, or maybe you're just curious about how molecules transform, why some react in a flash while others take, well, ages, this is your shortcut, we're going to distill the key insights into kinetics and mechanisms. And to guide us, we have our expert.
It's great to be here. It really is a fascinating journey. And uncovering these molecular pathways, it's like chemical detective work, isn't it? We look at the clues, the experimental evidence to figure out the most likely mechanism, always remembering, of course, that a mechanism is a model, our best explanation based on what we observe.
That's a great way to put it. Okay, let's dive in. Maybe start with the most common transformation. Ligand substitution reactions. So, simply put, what's actually happening here?
Right. At its heart, ligand substitution is basically a molecular swap. You have a Lewis base that's just an electron pair donor, remember, and it displaces another Lewis base from the central metal atom, which is acting as a Lewis acid, an electron pair acceptor.
So a new electron donor comes in, pushes out the old one.
Exactly. Think of it like swapping dance partners. A new one politely cuts in. A common example you might see is a water molecule attached to, say, a cobalt ion in solution being replaced by a chloride ion.
Got it. Swapping partners. Now, you mentioned some swaps are super fast, others incredibly slow. This brings us to lability versus non-lability. What's the difference, and why is it so important?
Okay, this is key. Lability and non-lability are kinetic terms. They're all about the speed of the reaction, not how stable the complex is overall, thermodynamically speaking.
Okay, speed, not stability.
Right. A complex is called labile. If it reacts quickly, substitution happens fast. If it reacts slowly, it's non-labile. That term replaced the older word inert, which was a bit misleading. It all comes down to the activation energy barrier. How high is that energy hill the complex has to climb to react?
So high barrier, slow reaction, non-labile. Low barrier, fast reaction, labile. Makes sense. Are there, general trends across the periodic table? Can we predict this?
Yeah, absolutely. There are some pretty clear patterns. For instance, S-block ions, many F-block ions, and D10 ions like zinc or cadmium, they're usually very labile, very quick swaps. Then you look at the third series, the first row of transition metals. The Mi ions are often moderately labile. Copper-2 is a standout. It's often exceptionally labile because of its distorted geometry, the John Teller effect.
Right, I remember that.
But then when you get to D-block M ions, especially those with specific electron counts like D3 or low-spin D6, like chromium-3, cobalt-3, they really tend to slow down. They're often non-labile.
Why is that?
It's largely down to ligand-field stabilization energy, or LFSE. These configurations have particularly stable electron arrangements in an octahedral field, so there's a significant energy cost to disrupt that arrangement during the reaction. Also, the heavier 4 and 5D metals generally form stronger bonds and have larger LFSEs, making them pretty non-labile too.
You also mentioned nucleophilicity before. It sounds like basicity, but you said it's different.
It is different, yeah. Basicity is thermodynamic. How strongly does something want to hold on to or donate electrons at equilibrium? Nucleophilicity is kinetic. It measures how readily a Lewis base attacks a complex to start a reaction. It's about the rate of attack.
Gotcha. Rate versus equilibrium strength.
Exactly. And one more thing to keep in mind here. The other ligands attached to the metal, the ones not directly involved in the swap, we call them spectator ligands, they can still have a big influence on how fast the reaction goes.
Okay, so we know what substitution is. Now, the big question, how does it happen? What are the actual step-by-step pathways?
Right, the reaction mechanism. That's the sequence of elementary steps. And usually there's one step that's slower than all the others, the rate-determining step, which controls the overall speed. For ligand substitution, we generally classify mechanisms into 3 main types.
Okay, what's the first one?
First up is the dissociative D mechanism. Imagine the complex MLNX. The first thing that happens is the leaving group X just leaves. It dissociates.
It breaks off first.
Yep. You form an intermediate, MLN, with a lower coordination number, an empty spot, basically. Only after that empty spot is created does the new incoming ligand, Y, jump in. Think of it like someone leaving the dance floor before their replacement steps on.
Okay, dissociate first, then associate. What's the opposite?
That would be the associative A mechanism. Here, the incoming ligand, Y, attacks first. It coordinates to the metal, forming an intermediate, MLN-XY, with a higher coordination number. It gets crowded for a moment.
More crowded first.
Right. Both the incoming and outgoing ligands are attached briefly. Then, the original ligand, X, leaves. So associate first, then dissociate. Like the new dancer joins the group, making it crowded. Then the old one leaves.
And the third type, the interchange mechanism.
The interchange mechanism is sort of in between. The leaving group departs as the entering group arrives. It's a single concerted step. There isn't a distinct detectable intermediate with a different coordination number. Instead, you have a transition state where the old bond is breaking and the new bond is forming simultaneously.
So like a smooth handoff.
Kinda, yeah. Picture XMLNY in the transition state. The distinction between A and I can be subtle. It often comes down to whether that intermediate state, MLN-XY and A or MLN and E, is stable enough to be detected, even fleetingly. If not, we usually call it interchange.
That makes sense. Now, within these A, D, and I types, you can also talk about the rate-determining step being A or D. What's that about?
Right, this adds another layer. We classify the activation process as either associatively activated, A, or dissociatively activated, D. If it's A, the rate depends strongly on the incoming group, Y. Its identity, its concentration, they matter a lot. This tells us that forming the new MY bond is really important in reaching the transition state energy.
Okay, A means the incoming group is key for the speed.
Correct. And if it's D, dissociatively activated, the rate is largely independent of Y. It doesn't really matter what Y is or how much of it there is. The speed is mostly determined by the breaking of the bond to the leaving group, X.
So D means breaking the old bond is the bottleneck.
Exactly. So you can have combinations like IA, interchange associatively activated, or IA, interchange dissociatively activated. And similarly for D and A mechanisms, though AA and DD are the most common ways to think about pure A and D. It helps us pinpoint where the energy barrier really lies.
Let's zoom in on a specific geometry now. Square-planar complexes. Why are these studied so much for substitution?
Good question. Square-planar complexes, especially things like platinum-2, are often sterically quite open. They're not too crowded. This makes them sort of prone to associative mechanisms where the incoming ligand needs room to approach. Plus, their reaction rates are often in a convenient range, not too fast, not too slow, easy to measure in the lab.
Makes sense. And their rate laws can be a bit complex, right? Showing parallel pathways.
They can, yes.
Yeah.
You often find rate laws that look something like rate, Kr1 plus Kr2y complex. This suggests two things happening at once. One path, related to Kr2, clearly depends on the concentration of the incoming ligand Y, which points towards an associative step involving Y.
Okay, but what about that first term, Kr1? It looks like it doesn't depend on Y. Is that a dissociative pathway then?
That's what people thought initially. But it turns out that Kr1 pathway is usually also associative. It's just that the solvent is acting as the initial incoming ligand Y.
The solvent itself attacks.
Yeah. The solvent molecule performs an associative substitution, kicking out X. Then your intended ligand Y, which is usually present in much higher concentration or is a better nucleophile than the solvent, rapidly substitutes the solvent molecule. So even that apparently Y-independent pathway is typically an associative process involving the solvent first.
That's sneaky. So the solvent gets involved directly. We talked about nucleophilicity, how good a ligand is at attacking. Can we put numbers on that?
We can actually. For platinum-2 chemistry, there's the nucleophilicity parameter, NPT. It's a quantitative scale that compares how reactive different entering groups Y are towards a specific reference platinum complex. It's quite remarkable these NPT values span almost 9 orders of magnitude. Huge differences in reactivity.
Wow, 9 orders of magnitude.
Yeah. And interestingly, high NPT values often correlate with ligands that are considered soft Lewis bases, ones with large, easily polarizable electron clouds. There's also a related term, the nucleophilic discrimination factor, S. This tells you how sensitive a particular complex is to changes in the incoming nucleophile. A high S value means the complex really cares about how good the incoming nucleophile is.
Okay, let's stick with square-planar. There's a really famous effect here that tells us a lot about the transition state, the trans effect. What is that?
The trans effect is absolutely crucial in square-planar chemistry. It states that the ligand trans, or directly opposite to the leaving group X, has a major influence on the rate of substitution of X.
The one opposite matters most.
Dramatically so. It's actually a combination of two things. There's the trans influence, which is a ground state effect. Some ligands weaken the bond to the group trans to them, making it easier to break. And then there's a transition state effect, where certain ligands, especially good π-acceptors like CO or cyanide, are particularly good at stabilizing the 5-coordinate transition state that forms during associative substitution.
So it weakens the bond before reaction and stabilizes the intermediate state during reaction.
Precisely. And this isn't just some academic curiosity. The trans effect is incredibly useful synthetically. Chemists use it to direct reactions. For example, you can make cis or transplatin, the famous anti-cancer drug isomers, by starting with either PTCl42 or PTNH342+, and carefully choosing the order you add the ammonia or chloride ligands, leveraging the trans effect series, which ranks ligands by their ability to direct substitution trans to themselves.
That's a fantastic example of how fundamental understanding leads to practical applications. What about just plain bulkiness steric effects?
Sterics definitely play a role. Big, bulky ligands can hinder associative reactions because they physically block the path for the incoming nucleophile. Makes sense, right?
Yeah, it gets in the way.
But maybe counterintuitively, steric crowding can actually accelerate dissociative reactions. If the complex is very crowded, losing a ligand relieves that steric strain, making the transition state to the less crowded intermediate more favorable.
Yeah.
So bulkiness hinders A, but helps D.
Interesting. And what about the geometry? If you start with a cis square-planar complex, do you end up with cis or trans?
For square-planar substitution, the geometry is almost always retained. Cis stays cis, trans stays trans.
Always.
Well, almost always is safer in chemistry. But the high degree of retention is strong evidence for an approximately trigonal-bipyramidal transition state. Imagine the square plane tilting. The incoming group, the leaving group, and the ligand that was transposed, the leaving group, all end up in the trigonal plane of this TBP structure. The other two original ligands are then above and below this plane. This geometry allows the swap to happen without scrambling the relative positions of the remaining ligands.
Fascinating. Okay, let's shift gears now to the other major geometry, octahedral complexes. You said earlier these almost always react via an interchange mechanism. So what's the main question we ask about them?
That's right. Interchange is the name of the game for octahedral. The key question becomes, is it associatively activated, IA, or dissociatively activated, ID? Is the transition state forming primarily because the new bond is starting to form, or because the old bond is starting to break? That's the main distinction we try to make.
And how do we model this process? Is there a standard mechanism?
Yes. The Eigen-Wilkins mechanism is the standard model here. It's essentially a two-step process. First, the incoming ligand Y and the complex ML6 rapidly bump into each other and form an encounter complex, ML6Y. This is usually a fast pre-equilibrium.
They just get close first.
Exactly. Then the second slower step is the actual interchange within that encounter complex where Y replaces X. Because the first step is fast, the overall rate often depends on both the concentration of the complex and the incoming ligand Y, but also on the rate constant for that internal substitution step.
It's a typical example.
A classic example is the reaction of the nickel hexaquion, LiOH2 62 plus Aaron, with ammonia. They form an encounter pair first, NOH262 plus Air NH3, and then more slowly the ammonia replaces one of the water ligands.
What does the rate data usually tell us for these kinds of reactions?
Often for complexes like the nickel hexaquion reacting with various different nucleophiles, the rate constant for that internal substitution step, Kr, turns out to be remarkably similar regardless of which nucleophile you use.
The incoming group doesn't matter much for the rate.
Exactly. And that strongly suggests an ad-mechanism dissociative interchange. The rate-determining step is primarily governed by the breaking of the NiOH2 bond, not by how good the incoming ligand is at attacking.
So for Ed, the leaving group is critical. Did the spectator ligands matter too?
Oh, absolutely. In dissociatively activated mechanisms, spectator ligands that are stronger sigma donors, better at pushing electron density onto the metal, can help facilitate the breaking of the MX bond. They sort of help push the leaving group off.
Makes sense. More electron density helps kick it out.
And steric effects work similarly to how we discussed before. Bulky spectator ligands create crowding. This crowding is relieved when you go to the 5-coordinate transition state in a dissociative process. So steric bulk favors dissociative activation, i.e. in octahedral complexes too.
Is there an energy term specific to octahedral reactivity like the LFSC you mentioned?
Yes, the ligand-field activation energy, LFAE. It's basically the change in LFSE when going from the ground state reactant to the transition state, LFSE. If forming the transition state involves a significant loss of stabilization energy, a large positive LFAE that contributes significantly to the activation barrier, making the complex non-labile, things like Ni, Thu, or V often have large activation energies, partly due to this LFAE contribution.
Okay, before we leave substitution, there's that interesting case, base hydrolysis, hydroxide ions speeding things up, but indirectly.
Right, the OH anomaly, it's a classic. If you have an octahedral complex with ligands that have acidic protons, like ammonia and H3 ligands, and you add hydroxide, OH, the substitution rate can increase dramatically, sometimes by orders of magnitude.
But the hydroxide isn't the incoming ligand.
Nope. Isotope labeling studies clearly show that water from the solvent is still the entering group, not the hydroxide ion itself.
So what is the hydroxide doing?
It's acting as a Brensted base. This is the conjugate base mechanism. The OH plucks off a proton from one of the ammonia ligands, turning NH3 into an amido ligand in NH2.
It deprotonates a ligand?
Exactly. Now you have a complex with an NH2 ligand. This conjugate base has a lower positive charge or even negative charge, which makes it easier for the negatively charged leaving group, like Cl, to depart electrostatically. Plus, the amido NH2 ligand is a very strong pi donor. It can donate electron density into empty metal orbitals, which strongly stabilizes the 5-coordinate transition state formed during the now easier dissociation step.
Wow, so the hydroxide facilitates leaving group departure and stabilizes the transition state, all by acting as a base first.
Clever, very clever mechanism. It shows how subtle effects can have huge impacts on rates.
Okay, we've covered ligands swapping places really thoroughly, but complexes also trade electrons, right? Let's shift to redox reactions. How are these classified?
Yeah, electron transfer is fundamental.
Yeah.
The major breakthrough in classifying these for coordination complexes came from Henry Taube. He proposed 2 main mechanistic pathways.
2 main types.
Yes. The inner sphere mechanism, where the 2 reacting complexes are linked by a common bridging ligand in the transition state. Often, an atom is actually transferred along with the electron. And the outer sphere mechanism, where the complexes just come into contact and an electron tunnels between them without any shared ligand or covalent bond changes in the intercoordination sphere.
A bridge versus no bridge. Let's start with the inner sphere. What's the definitive experiment that proved this happens?
The classic experiment involved the reduction of co-Cl NH352+ by Cr2 plus Aq. The product containing chromium was found to be CrCl OH2 52 plus Day2. Crucially, the chloride had to have come from the cobalt complex. If you added radioactive chloride ions, 36Cl, to the solution, none of it ended up in the chromium product.
So the chloride definitely acted as a bridge for the electron transfer.
Exactly. It proved that the chloride ion was transferred directly from cobalt to chromium during the redox event, serving as a bridge.
How does that happen step by step?
It's generally thought to occur in stages. First, the oxidant and reductant form a precursor complex. Then the bridged intermediate forms. Then the electron transfer occurs through the bridge. This creates a successor complex, which is still bridged. Finally, this bridged successor complex breaks apart to give the final products.
Which step is usually the slowest?
Most often, it's the electron transfer step itself through the bridge. But sometimes, if both metal centers become non-labile after the electron transfer, the breakup of that successor complex can be the slow, rate-determining step.
Okay, so inner sphere needs a good bridging ligand. What about outer sphere? How does an electron just jump across space?
Well, it's not quite jumping across empty space, but tunneling. In the outer sphere mechanism, the electron transfers between the 2 complexes while their inner coordination spheres remain intact. The key idea here comes from the Frank-Condon principle.
That sounds familiar from spectroscopy.
It is. It states that electron transfer is much, much faster than nuclear motion. So the electron transfer happens essentially instantaneously, but only when the nuclei of both complexes and the surrounding solvent have momentarily fluctuated into exactly the right geometry, a configuration where the energy of the system before and after electron transfer is the same.
So the molecules have to vibrate into a magic shape first.
Sort of, yes. They have to reach a specific nuclear configuration, the transition state geometry, through thermal fluctuations. The energy required to get to this configuration is the activation energy. Marcus theory provides the mathematical framework for this. The rate depends on the overall thermodynamic driving force, how much energy is released, and something called the reorganization energy.
Reorganization energy, what's being reorganized?
2 things mainly. The inner sphere reorganization energy is the energy needed to change bond lengths and angles within each complex to reach the transition state geometry. The outer sphere reorganization energy is the energy needed to rearrange the surrounding solvent molecules. The electron transfer can only happen efficiently when both the complexes and the solvent are arranged just right.
So small reorganization energy means faster electron transfer.
Generally, yes. Reactions are faster if minimal structural changes are needed in the complexes and the solvent upon electron transfer. This often happens if the electron is going into or out of non-bonding orbitals, or if the metal centers are well shielded from the solvent.
Marcus' theory led to some surprising predictions, didn't it? Like the inverted region.
It certainly did. The Marcus inverted region is one of the most fascinating predictions. The theory suggests that if a reaction becomes extremely favorable, thermodynamically very, very large negative Ag degrees, the reaction rate should actually decrease again.
Wait, making it more favorable makes it slower. How does that work?
It seems totally counterintuitive, but think about the energy diagrams. For very exothermic reactions, the potential energy well of the products is much lower than the reactants. To find the intersection point needed for electron transfer, where energies match, you actually have to climb higher up the reactant energy well than you would for a moderately exothermic reaction. It took a while, but this inverted behavior has been experimentally confirmed.
And it's important biologically.
Hugely important. In photosynthesis, for example, there are electron transfer steps that are highly favorable. Nature uses the inverted region effect to deliberately slow down unwanted back electron transfer reactions, preventing the captured light energy from being wasted. It's an amazing example of molecular tuning.
Incredible. Okay, one last area, photochemical reactions. How does light change the game?
Light adds a huge packet of energy. A photon absorption can dump 170 to 600 kilojoules per mole into a molecule. That's way more than typical thermal activation energy, so it can open up completely different reaction channels that just don't happen in the dark.
How do we categorize these light-induced reactions?
We often talk about prompt versus delayed reactions.
Prompt means fast.
Very fast. Prompt reactions happen almost instantly after light absorption, usually in less than 10 picoseconds. The excited state falls apart or reacts immediately. A classic example is chromium hexacarbonyl, CrCO6. Shine UV light on it, and a CO ligand dissociates extremely rapidly. The efficiency, the quantum yield, how many reactions per photon absorbed, often goes up if you use higher energy photons.
Okay. And delayed reactions.
Delayed reactions involve excited states that live much longer, microseconds, milliseconds, sometimes even longer. You can think of these long-lived excited states as energetic isomers of the ground state molecule. They hang around long enough to bump into other molecules and undergo reactions that the ground state wouldn't.
Like a temporary superreactive version of the molecule.
Exactly. A famous example is the ruby p32+ complex. Its excited state lives long enough to act as both a strong oxidant and a strong reductant, enabling all sorts of useful photoredox chemistry. Light creates a new chemical personality, essentially.
Can we roughly predict what kind of reaction light might cause based on the type of electron transition?
There's a useful, though not perfect, rule of thumb. DFD transitions, where an electron just moves between different d orbitals on the metal, often rearranges bonding to the ligands. These tend to lead to photosubstitution, swapping ligands, or photoisomerization, changing the geometry.
Okay, DFDD leads to structural changes. What about charge transfer?
Charge transfer transitions, where an electron moves significantly between the metal and a ligand, either metal to ligand, MLCT, or ligand to metal, LMCT, involve a major shift in electron density. These are more likely to initiate photoredox reactions, where the complex gets oxidized or reduced.
But you said it's not a perfect rule.
No, chemistry loves exceptions. You can find examples where charge transfer leads to ligand loss or where DFD excitation facilitates a redox process. But it's a good starting point for thinking about how absorbed light energy gets channeled into chemical change.
What about systems with metal bonds? What happens when light hits those?
If you excite an electron into a metal-metal antibonding orbital, that can certainly weaken or break the metal-metal bond, leading to photodissociation. But perhaps more interestingly, exciting these systems can lead to multi-electron redox photochemistry.
Multi-electron.
Yeah, transferring more than one electron in a photochemical step. Take the PT-POP complex, PT2, P2O5H2, 44. That's two PT2 ions bridged by ligands. In the ground state, there's no PT-PT bond. But if you excite it with light, you promote an electron into an orbital that is actually bonding between the two platinum atoms.
Light creates a bond.
Effectively, yes, in the excited state. This excited state is surprisingly long-lived and becomes a powerful two-electron reducing agent. It can react to form a PT3 species, which does have a formal PT-PT single bond. It's a beautiful example of light completely changing the bonding and reactivity.
That's amazing. This has been an absolutely incredible journey through the really dynamic world of coordination complex reactions. From ligand swapping places, sometimes fast, sometimes slow, to electrons tunneling across barriers and light triggering entirely new pathways, it's clear that understanding these precise molecular mechanisms is key. So, just to quickly recap our deep dive, we looked at the crucial difference between labile and non-labile complexes and the kinetic factors like LFSC that control reaction rates. We unpacked the main substitution mechanisms, dissociative, associative, and interchange, and how we classify their activation, A versus D. We saw how square-planar complexes gave us insights like the incredibly useful trans effect. For octahedral complexes, we discussed the Eigen-Wilkins mechanism and the clever conjugate-based mechanism for base hydrolysis. Then we moved to redox, distinguishing inner sphere, bridge from outer sphere tunneling pathways, guided by Marcus theory and its surprising inverted region. And finally, we touched on photochemistry, how light drives prompt and delayed reactions, often linked to dilate or charge transfer excitations. It really makes you think, doesn't it? And maybe this is a final thought for you, our listener. How might a deeper, more refined understanding of these precise molecular dances, these mechanisms we've talked about, allow us to, say, design much more efficient catalysts, or maybe better materials for capturing solar energy, or even fine-tune processes within biological systems? The possibilities, well, they seem pretty vast. Thank you so much for joining us on this deep dive into the reactions of coordination complexes. We hope you leave feeling a bit more informed and definitely a lot more curious about this amazing molecular world.